Roger's going to be talking today to us. He's a grad student in CSD who works with data recruiters.
Hi everyone, I'm going to tell you today about data streams with pattern deletions. And this is where I work with data recruiter. So data streams are a model of computation that has seen increasing prevalence because big data, explosive data, and so forth. So they can model, they show up in a lot of different domains. So for one of the most used domains of data streams are internet traffic logs. When you have a large stream of data, IP address sends one packet to this other IP address, just coming at a very fast rate. Other examples are financial transactions, large experiments like large LHC generate these huge data streams with terabytes of data, and then distributed sensor networks, and there's also a bunch of applications and databases. So the classic model is you have some vector f in Rn, and generally you want to think of n as just being ginormous, like several billion, so something that's way too large to store in memory. And at the beginning, it's initialized to 0. So, for instance, on the last slide, coordinate f could represent the number of connections outgoing from IP address. So fi would be the number of connections outgoing from I, or fi I could refer to a pair of IP addresses. With the number of connections today between IP address, I and j, and then you have like the square of the number of coordinates. So n is really large, and at every time step, f receives updates coordinate-wise. So at time t, you're going to get an update index it, which is the coordinates, and then there's an update delta t. And this is going to cause the change of updating the current value of fit by delta t. So there's two real fundamental types of these streams that are studied. That first natural one is you restrict these deltas to be strictly positive, then you get insertion-only streams. I'm only inserting things into these coordinates. And then you can also consider streams where the updates can be positive and negative. Of course, if they're integers, simplicity, and they're going to be bounded by some integer big M. And the length of the stream is going to be little m. And an assumption that's made pretty much everywhere in the literature, but you can work without this assumption, it's not necessary. But the simplicity is that everything is polynomial in n. Really, we're going to be taking logs, so that means log of m, log of n, big O notation. So the goal of almost all these problems in data stream literature is to compute approximations, certain functions of f, using only log n space. Instead of, obviously, for almost all these questions, you can store the whole vector and solve problems with it, but you don't want to do that because that is too large. So that was just an overview of the model. So, like examples, you have some vector, high-dimensional store. It's going to start receiving coordinate updates. Update the fourth coordinate by 1, and then get other updates. The turnstile stream, meaning that you have some negative updates, have some more negative updates, and then some more updates. And then, for instance, at the end, we could ask, okay, I've had a bunch of updates. What's the p norm? That's an example question. What's the sum of the p powers of all these entries? It's called p norm estimation. Okay, so a bunch of problems that two of them in this order, but probably the most studied problem is the heavy hitters problem, also known as elephant queries or identifying frequent items. So basically, for the L1 guarantee that says that I want to return to you all the items, all the coordinates that comprise at least an epsilon fraction of the total L1 mass. And there's also a condition that you don't return anything that's less than like epsilon over 2 times f. I mean, otherwise you could just return the whole set, right? And then there's a similar condition for L2, which is do the same thing, but instead of epsilon fraction of the L1, it's epsilon fraction of the L2. So now, so it's actually pretty easy to show that the L2 problem is a lot harder problem, because here you're basically asking to determine within epsilon f1 error whether something, like determine item's frequency to epsilon f1 error, and here you're being asked to determine item's frequency to epsilon f2 error, and as we know, f2 can be a lot smaller than f1. It can be square root of n times f1, 1 over square root of n. So this is a much harder problem in general. So then there's LP norm estimation that I talked on the last slide, basically. You want to estimate the LP norm of the vector. For p equals 0, this corresponds to estimating the size of the support, the number of non-zero coordinates in the support, called L0 estimation, and then there's a bunch of other study problems, such as sampling according to the LP norm, estimate the entropy of the vector, just considering the vector to be a probability distribution, and then estimate the interproduct of two of these vectors. So the observation that got this work started was that there's a bunch of all these problems that have been studied in the literature the last 20 years, but between these problems, there appears to be exactly a log n gap between the complexity, the space complexity required to solve problems in the turnstile setting where you're allowed to have deletions, and in space complexity where you're not allowed to have deletions. So, for instance, for the heavy hitters problem, the one that I just defined, if you allow deletions, you need absolutely the lower bound of block squared n, but you are looking at insertion-only streams, you can do it with log n space. And this occurs for, as you can see, almost every other problem here. It's almost always, it's a log n gap in every single instance, except for this case where the epsilon squared and log n are split. But this is also known to be tight, so essentially there's a log n gap, multiplicative in all these problems. And so you kind of, I'm not going to get into quite how these lower bounds come from, but the essential idea is the lower bounds come from you have some stream, and you insert a large number of items. So that at the end of the day, the L1 mass is about n, order n or poly n, and then you delete almost all of them, at least n fraction of them. So in other words, these lower bounds come from turnstile streams that allow deletions, where the final norm is nearly 0, but there's been a lot of updates in the stream. So the signal size you're trying to estimate is, poly 1 over n times the actual noise in the stream, the amount of data that you had to process. So this is sort of the intuition for why you need more space with these turnstile streams. So the natural question that we asked in this work is, well, if you actually prevent these streams from deleting everything, if you, they're still allowed to delete stuff, but you bound the number of deletions in some way, can you actually get better algorithms? And the goal of this work is to say, yeah, in almost all these problems, you can get substantially better algorithms in actually a very nice parameterized way. So I'm going to introduce the bounded deletion model now. So you can just introduce these two natural vectors, I, j, and dj, or I and d, where I is the stream, but you're going to restrict it to positive updates. So ij is the sum of all the positive updates that were received to I, and received to j, and dj is the sum of all the negative updates that were given to j. But then you take absolute values so that these are both positive vectors. So then our frequency vector is just the difference between these two things. It's a really natural way to define it. So we're going to bound deletions as follows. We're going to say, the bounded deletion model is, I'm going to give you some parameter alpha, and we say f is alpha bounded if the L1 norm of I plus d is at most an alpha times f. So it's always going to be greater because I and d are both positive, and f is the difference. So in particular, if you force alpha to equal 1, then d actually needs to be 1. Because, there's a question? Sorry, that's what I meant. D needs to be 0. So what that corresponds to, alpha equals 1, is your stream is now an insertion-only stream. But on the other hand, if alpha equals like polynomial in n, then d can be also polynomial in n. These can be arbitrarily close. So now you have a turnstile stream. So alpha is like this parameter that goes between insertion-only and turnstile streams. For 1, it's insertion-only, and for poly n, it's turnstile. And we're going to consider all the updates for today just to be unit updates. It's actually equivalent to just consider all the updates are plus or minus 1. If an update is really big comes, you just expand it into a bunch of smaller updates, and it's the same thing. So in this scenario, it's actually much simpler. It says that the length of the stream is at most alpha times f, the L1. So like a little bit of intuition about what this looks like. You have your graph. This is the number of updates that you've had so far, and this is the L1 norm after T updates. So obviously, if your unit updates, the L1 norm can't be greater than the number of updates you've seen so far. So this line is an upper bound. But the alpha property just says that at the end of the stream, this line is a lower bound. So your alpha property says that you have some streams getting updates. It can go below this line, but it's going above it, and it can go below it again. But the guarantee is that at the end of the stream, when the stream is over at time equal n, the L1 norm is greater than alpha times n, or other way around. It's greater than 1 over alpha times n. So this is like how I like to think of the alpha property. Okay, so example of why this is actually maybe a reasonable model, just for some applicant motivation, I guess. So one of the reasons people use turnstile streams is to estimate the difference between two vectors. So, for instance, you have two routers that are routing traffic, Fi, F and G. F looks through the number of packets sent through IP address I, and G is the same, but for the second router. And you want to estimate the disparity, like, you know, how much is getting sent for one that's not for the other, vice versa. So what's the difference in traffic between these two routers? And the name of the game is that if this difference is, like, you know, not arbitrarily close to 0, if there's some signal that you're trying to estimate, then you can actually estimate it. It's an alpha property stream. So the alpha property means that the total number of traffic is the total amount of traffic is less than an alpha times the difference, meaning that if on average your coordinates differ by even, you know, 1,000th fraction, then alpha is going to be less than 1,000. So if you have like even like a little bit of fluctuation in the traffic between these two routers, you have alpha is only 1,000, which is a lot less than the universal size these etc. So just an idea of how this could be used. Okay, so here's a simple example of how we can do better in alpha property streams. Essentially, for L1, we have a corresponding definition for L0, but I'm only going to talk about L1 in this talk. Almost all of our improvements come from the fact that if you have this fact that that the final norm is at least an alpha fraction of the total stream, then you can actually sample to recover this bias. So I'm going to show that now. So suppose we have one item that's at least an epsilon fraction of the stream. It's a heavy hitter. We want to estimate it. So we want to estimate it. We know F has the alpha property. Because Fi is epsilon fraction of the L1, it just follows immediately from the definition that if you just consider this one item, it has the alpha over epsilon property. What I mean by that, by giving one item having the alpha over epsilon properties, I mean the number of updates that have been made to this index is at most alpha over epsilon times the final value of Fi. So what we're going to do is we're just going to sample updates and store the value in a counter. So we'll sample, if we sample an insertion, we'll say that's +1, we sample a deletion, we'll say that's -1, and we'll sample with some probability p. And then our estimator, which is unbiased, is just to take the counter that we sampled from and scale it back up by 1 over p. And so because we have this alpha property, we know that the expectation is bounded below. It's not arbitrarily small. And then you can just use Hopting bounds, general Hopting, to show that all you really need is poly alpha over epsilon samples in expectation to get a 1 plus or minus epsilon of our estimation. It's actually like alpha squared over epsilon squared, so it's not like some crazy polynomial thing. So this is just simple application of Chernoff bounds. If you sample, like you take a sample vector where it corresponds to taking alpha over epsilon, poly alpha over epsilon samples. Then if F has the alpha property, then for every single I with high probability, which is coming from the log n there, you get an epsilon approximation. So in other words, if I just implicitly store this vector and store poly alpha over of epsilon updates, then I would get an estimate that satisfies this. But we don't want poly alpha space, so we're gonna still have to use other sketching techniques to reduce the space. So I asked some brief intuition here why we're doing better. I think I already gave some though. But the idea is that a bounded deletion stream is so like there's some bias, or like every update is like kind of like flipping a coin. Heads is an insertion, tails is a deletion. But if you're in the turnstile model, the number of insertions and deletions could be the same. So the coin will be like completely unbiased, and you can't like really estimate that. You'll get like error. But on the other hand, if the bias is large enough, you can estimate it, and the error in estimating it will be proportional to its size, which you get from the alpha property, the fact that the L1 is not too small. Because the error you're going to end up getting is proportional to the number of updates, right? But our alpha property is bound to the number of updates by a fraction of the L1 mass. So if you make the error small enough as a function of the total number of updates, you're making the error small as an epsilon fraction of the L1 mass. So turnstile algorithms, at the end of the day, their final L1 mass could be in log n possible intervals of, constant factor approximations, which is how a lot of these algorithms work. They break it up into log n intervals, 0 to poly n. But for bounded deletion streams, at the end of the stream, we actually know that there's only log alpha possible scales, intervals of constant factor approximations that it can be in. And this is going to roughly allow us to turn these log n bounds and all the problems I showed you towards the beginning of this talk to log alpha bounds. And again, because alpha intuitively can be several orders of magnitude less than zero, even a constant, this is like, I guess, substantial space improvement. Again, alpha is like a multiplicative thing, so it's not saying that so if alpha equals 2 means I can insert 10,000 items and delete half of them, then alpha is only equal to 2. So it's not like I can delete only 2 of them. So it's not unreasonable to think that alpha can be a constant, I suppose. So to show how we can solve the heavy hitters problem more efficiently with these alpha streams, first I have to introduce a classic data structure called counting, used in a lot of other algorithms as well for the data stream literature. So algorithms isn't that complicated. So I'm going to initialize a table A with log n rows and k columns. K is going to correspond to our error. And so for every row, what I'm going to do is I'm going to take hash functions that hashes my items into one of the buckets in that row. And then I'm just going to take some random signs for every item as well. They only need to be like pairwise independent. And then what I'm going to do is when my updates come, I'm just going to hash the stream into these buckets along with these random signs. So I'm going to, update comes, I'm going to find what bucket it goes into in each row, and then I'm going to hash it and hash the update into that bucket, and I'm going to give it a random sign. Okay. So, and then the hypothesis says, if I want to estimate I, just look to all the buckets it hashed to, check what the value of that bucket is, multiply by the sign that I was in, that I had, just to make sure it's unbiased, and then take the median. And so this is all there is to the estimator. Just to show you what it looks like, you have some table. Each row, you hash the stream into the row, and then you do this for a bunch of repetitions. So an update comes, I hash it into the row. I'm updating one item, the item 1 by 2. So I'm just going to hash it into every single row. Sometimes getting random signs. And then I'm going to do it for another one. I get some random signs over here again. There's obviously some collisions in some of these values. Right? You're going to get collisions. I hash another thing, get some random signs, hash another value.
So are you hashing based off of like the time step in the stream, or are you hashing based off of
I'm hashing
index?
I'm hashing the universe size, so the coordinates. So each coordinate, so for every row, each coordinate goes to a unique bucket. So it has nothing to do with the time step. Yeah, so sorry, I didn't mention this earlier, but in the data stream model, you get no guarantees on the order of updates. You can basically have to assume that they're adversarial. So you really don't make many decisions based off of the updates. Update number, that is. So you hash every update into a bucket based off of the index that's getting updated, and then you do this for log n repetitions. And then at the end, at the times f1, I updated f1 by 2, and then at times f4, I updated f1 by 4. And now I want to estimate what's the actual value of f1. It's actually 6, but how do I estimate it? Well, I look at all the buckets that f1 hashed to, and then I take the median of them scaled by these random signs. If f1 got a random sign, I'm hashing into it. And then I return that as my output. So in this case, I actually get the exact answer back because I haven't really added any things here. in general, you get some error. And I'm going to tell you what the error is really briefly.
Sorry, can you say, what is the idea behind random signs? Like,
Okay, so yeah, actually I'm going to tell you that right now.
Okay.
It might help if I actually wrote this down. Is there chalk? So let's focus on one row for now. Count sketch is basically partitioning all the updates to this vector into k buckets, and then it's hashing all the updates to the things that hash into one of them into the bucket. So you're basically splitting the stream into k buckets and just throwing everything in the stream with random signs. So when you estimate, take an estimate of an item from a bucket, you multiply that by that sign. So what you're going to end up with in a bucket, like just say aij is one bucket, and suppose that fk went into this bucket, and I want to estimate fk. Well, I'm going to multiply this by like g of k. This is the random sign that k gets in this bucket. So what you're actually going to get is the random sign was going to cancel that this was in. So the estimator is fk plus gk j times the sum of everything else that collided. So fi need some other sign. You get the idea. Basically, everything else that collided, and you have a random sign here and a random sign here with a 4 y's independent. The expectation multiply. So the expectation of this whole thing is 0.
2 y's is enough.
2 y's is enough for the expectation, yeah. The expectation of this thing is 0. So that means that it's an unbiased estimator, first of all. But then use the 4 y's independence to use the variance, right? So the variance, so the expectation of the error is 0, but the variance of the error corresponds to the squares of these things. So it's going to be the L2, but then you're dividing by the number of buckets because you're splitting up the L2 into k buckets. So the variance is the L2 divided by k. So by using Chebyshev's inequality, the error is square root 1 over k times the L2 with constant probability. And this is for one row. So what does count sketch do? Well, it says, okay, the error, with constant probability, 2/3, I get a good estimate. So I'm just going to repeat this log n times and take the median. And by Chernoff-Hofting again, with high probability, you get the bound that you wanted. Okay, yeah. So the bound that you actually get is actually slightly better. This is the theorem of from count sketch. The error on all coordinates that you get from count sketch is less than the tail of the L2, where the tail is the L2, but you've removed the top k heaviest coordinates. And it's actually not hard to see why this is true. Basically, you at the beginning, before you make this argument, you say, okay, well, let's look at the top k biggest items, and like just suppose for constants that I take 6k rows or something like that, or 10k columns. Well, then with constant probability, those k largest things, when I'm estimating some item, they're not going to collide. They're going to be hashed to other buckets. So I can repeat the same argument conditioned on the fact that the thing that I'm trying to estimate hasn't collided with any of these biggest items. And then I get this tail error. And it turns out that this tail error is actually pretty helpful when it comes to, because this can be, for certain vectors, this can be a lot smaller. Basically, recall the heavy hitters problem, which said that we want to return an S, a set of items, such that contains all the items that are epsilon heavy hitters, and it doesn't contain any items that don't have at least epsilon over 2 of the LP nabs. So the error of count sketch is strictly less than epsilon times F2 if you set k to be 1 over epsilon squared. So setting the number of columns to be 1 over epsilon squared, you solve L2 heavy hitters. And then I'm not going to really say why, but like it's fairly straightforward to see that just using, just figuring out where the L2 is maximized. If you look at the tail, it's always going to be less than 1 over square root k times the L1. So the error of count sketch is actually 1 over k times the L1. So just setting k equals 1 over epsilon, you solve L1 heavy hitters. So these two are type bounds for the two L1 and L2 heavy hitters problem in the general turnstile case. So our goal is going to be to adapt this data structure via sampling to the bounded deletion setting where we can do better. And our main improvements are going to come from the fact that our counter sizes are going to be smaller. one of our epsilon columns, and each bucket is a log n integer, log n bit integer, or whatever. So the complexity is 1 over epsilon log squared n. And what we're going to do by sampling is actually reduce the sizes of these counters. And so by reducing the sizes of the counters, we save a log n factor and change it to log alpha. So here's like the naive algorithm of what we would want to do. Well, we showed earlier that if I just sample poly alpha over epsilon updates, I actually am going to estimate all the coordinates to an additive epsilon f1 error, right? That was one of the first things I said earlier. And I just showed you now that this count sketch data structure, it actually gives you, it also gives you error epsilon times the L1. So why don't I just take a uniform sample of a stream and then just toss into count sketch? Like, shouldn't that be in? Go ahead.
So you don't change the size of the data structure, right? You're maintaining it.
No, I'm not changing the size of the data structure.
Changing the kind of.
Yeah. So like on the bit level, you sample. You're eventually gonna sample in some way. So the buckets, the counter sizes are reduced, so they can be stored in log alpha bits. But then your actual estimate is going to be scaled up by, there's sample probability p, but you can just store the probability p like separately. You don't need to multiply it by all the buckets. So this is how you get less space. So again, because if we sampled poly alpha over epsilon updates, then our buckets are going to correspond to poly alpha over epsilon updates. So it takes log of that bits to store it. Again, the log n, this extra second factor of log n comes from getting high probability. Okay, so there's a couple problems with this. But the first problem is that, like I said, you're given no assumptions at all on the length of the stream or the ordering of the stream. So we don't actually know the stream in advance, and so we can't sample uniformly from it. And if we tried to do so, and we ended up like a lot of these arguments require uniform samples, and our counters require the fact that we can take too many samples, so we can't underestimate.
Can you do something like reservoir sampling?
Reservoir sampling will give you like one uniform sample from the stream, or k is constant.
We need that for every.
Yeah. Because we're not actually like paying attention. Like we see an update and we're gonna say flip a coin, some bias coin side, another one to sample it. If we do sample it, we put it in the bucket, and we reservoir sampling keeps it. Yeah, exactly. So okay, so here's so I just said that basically we don't know the length of the stream, so we have to deal with that in some way. So there's a couple of ways of dealing with it. The one we're going to use here, just for the because this actually works well with other algorithms, is we're going to split all our buckets in count sketch into positive and negative parts. So after t steps, let AT be the state of the count sketch. We're just going to split it into positive and negative parts. Put the positive updates that would have gone into AT into the positive part, put the negative in the negative part. So then AT is just the difference. And so what we're going to do is set big S to be some large integer polynomial in alpha, log n, and epsilon. And that's going to be like our expected sample size, how many updates we want to sample. And then every time step where the time step is S or 2S or 4S, every time it doubles from S, we're just going to replace the value of the counter by binomial variable with the expectation 1/2. And in other words, like if I have 10, I'm gonna like flip a coin 10 times with probability 1/2 and keep the number of heads I get. So obviously you could do this and space the size of the counter to begin with, and with high probability the counters are never going to get much larger than their expectation, which is S. Like note here that the expected number of after 2 to the k times S steps, the expected number of updates is always going to be S because we're reducing it by 1/2 every time it doubles. So it's actually fairly easy to show. This is just the same as if I was actually going to take a uniform for one row. Doing this is the same exact thing as sampling uniformly from the stream for that row, taking a uniform sample and hashing into the row. The difficulty is that for different rows, like for each row, we've now taken a uniform sample and hashed into the stream. But for different rows, they no longer correspond to the same sample, because the buckets in one could contain like half of something that goes into the other, and so maybe you sampled one update by keeping it in one bucket, but you didn't in the other row. And if you do that, then you're no longer looking at one sample. You're looking at a different sample for every row, for each of your log n rows. In other words, so let SI be the vector of samples corresponding to the ith row of your count sketch. Then the error in that row for estimating Sij, like a coordinate of Si, the error coming from count sketch is the count sketch error. What is a count sketch error is a function of the sample. It's the L2. It's not the L2 of the frequency vector because you're not hashing the frequency vector in. You're hashing the sample in. So now your error each row is a function of a different sample, and you need to show that these samples are this error is comparable to the L1 because we're trying to solve the heavy hitters problem. So we want our error to be epsilon times the L1. So we know that our error from count sketch is the tail of the sample, and we know that from our sampling lemma that the actual sample estimates the true value pretty well. Actually, it estimates it with high probability. This epsilon here just factors into a log at the end. So we can actually get really good estimates here in terms of the L1. So every sample is a good estimate, actually. So it actually doesn't matter that, what you argue is that it doesn't matter that we're looking at different samples. With high probability, every sample is a good estimate. So our actual estimate, which is taking the median from all these rows, just like you do in count sketch, well, you get the error from all the samples being good, and then you get this error, which is, well, so the error from each of them is the tail of the sample vector. So the error from all of them for each row satisfies it's at least the error of the max one, right? So you take with high probability you get this. The issue is this is still in terms of the maximum L2 error. And what I told you earlier is that sampling preserves the L1. So you sample, with enough samples, you can preserve the L1 to add into epsilon. But it's not clear that sampling preserves the L2. And in fact, it doesn't in general. So you have to show that this value here is small. You have to show that the tail of the sample vector, or in general the L2 of the sample vector, isn't too much larger than the L2 that you're looking at to begin with. Okay, so you can do this. It's actually not terribly difficult. It's just a variance of Bernstein bound. But you show that, okay, so the L2 is not going to be preserved up to an epsilon fraction. And the justification is that when you're sampling, if like there was some small probability you sample something that had relatively decent sized L1 mass compared to the total norm, but with in L2 it's very small. So then that thing, when you scale it up by P inverse, it's going to blow up. And so that's going to cause you a lot of error. And the error it's going to cause you is proportional to the probability that you sampled it, which is proportional to the L1. So you're going to get error. You're going to get the L2, the actual L2, but you're going to get error coming from the L1. But that's okay, because we already had error of the L1 anyway. You just apply this lemma, and then this whole bound here just becomes, let's see. So, in other words, with high probability, we said before, because the expected number of samples is at least log n with high probability, it's not going to be too much larger than log n times alpha and epsilon. So we repeat it, and the total space is k log n times the size of the counters. So here we have like two precision parameters, which is kind of interesting to note. We have our k precision parameter, which is going to give us the error here. So the more buckets we have, the smaller L2 error is going to be. And then the more samples we take, which is epsilon, the smaller our L1 error is going to be. So the theorem is, again, like just putting together what we just said, our data structure produces an estimate by sampling. It uses fewer bits because the counter sizes are smaller, and the error is proportional to k with the L2 norm, and epsilon times the L1 norm. And then again, epsilon has logarithmic dependence, and k has linear dependence. So if you wanted to actually get the bound here for L2, the normal estimator gives the normal count sketch. You could just set epsilon to be 1 over n, and then you know that this can't be more than square root n times bigger, and so then you get log n squared, which is exactly what count sketch gives. So if you want L2 error, you can't do better than count sketch. But if you're looking for L1 error, we actually do better than count sketch. Okay. So this is the same theorem. Again, if you look at the tail, it's at most another square root k factor. just by looking at the values that maximize the L2. So if you set K equals 1 over epsilon, you solve the L1's heavy hitters problem. The reason that is because then the error here is epsilon times the L1, the error here is epsilon times the L1. And so I can estimate coordinates with epsilon L1 error, and then I can distinguish what modulo constant factors, I can distinguish what items are epsilon heavy and what are not. So yeah, so we solve the L1's heavy hitters problem. So there's a lower bound for general streams of epsilon or epsilon, 1 over epsilon log squared n, so this beats that lower bound for small alpha. And it nearly matches. So we actually also have a matching lower bound for alpha property streams. And this holds for all alpha, even constant alpha. This shows that basically this is the best you can do. So the question is, we've shown that if you bound the number of deletions your stream can make, you can actually do substantially better for these alpha property streams. For constant size alpha, you can shave a log n factor. So how many can we do this for all the problems that have been studied in the data stream literature? And I think I have enough time to talk about another one we did, which is L1 estimation. This is a good one, which is just, now I want to just give you return one value, which is going to be a 1 plus or minus epsilon approximation of my actual L1 of the vector. So again, I'm going to tell you first about the algorithm that's used in general turnstile streams in the literature to solve this problem, and then I'm showing you how we can adapt it to get better space complexity. And the adaptation is going to be really similar. We're going to sample, and our counters are going to be smaller because we didn't take the entire stream. So that's where our space improvements are going to come from. It's actually a really cool algorithm. This classic algorithm basically relies, this works for NEP, for any of the LP norm, but we're going to just focus on the L1 norm. And so it uses Cauchy random variables. And these are kind of badly behaved, very heavy tail random variables. The PDF behaves like a quadratic for a large x. And so what that means is if you try to integrate it times x, both tails are infinity, so the expectation is undefined, doesn't have an expectation, and the variance is infinite. So you can't actually use concentration bounds of these things at all, but they do have this nice property, which is the one stability property, which is that if I take the dot product of a bunch of IID Cauchys with a bunch of constants, a1 to an, the result is distributed according to another IID Cauchy times the L1. And this fact is used roughly, this is the fact that's going to be used to estimate the L1 of the stream. So what we do is, for the moment, forget about the fact that M is going to be a huge matrix. Suppose we could store it with small space. So we're going to select an R by N matrix of IID Cauchys. R is going to be 1 over epsilon squared is what we need. And then we're just going to compute the dot product. And this can be done, basically what this corresponds to is, I kind of see an update. I find what Cauchy is multiplying that item, and then I scale, and then I put that into a bucket, and then I do that for every row. And that's how I get that. So this can be computed in the stream. And so I'm going to end up with some vector y, and y is going to be size r, so it's going to be 1 over epsilon squared. And in the general case,
How are you doing this in the stream? M is R cross N after whatever N
N is, sorry, what? So M is R by N, F is N by 1.
You don't store M explicitly?
Yeah, no, so basically, yeah, so I said for now, just assume that you could store M in small space. What we're going to, so originally, it was de-randomized using Nissan's pseudo-random number generator, but actually, you can just show that all you need is 1 over epsilon y's independence for these random variables, and so you can just generate them with hash functions. Yeah, so like basically you just use a bunch of hash functions to store all these. You're not going to have full independence, but I'm not skipping that issue for now. So if you had full independence, note that each bucket is going to be distributed like a Cauchy times the actual L1. So I'm going to have 1 over epsilon squared buckets, each is distributed like a Cauchy times the L1. And so our estimator is going to be take the median of all these buckets and then scale it by the median of the distribution. That's like a distribution median. And so for a Cauchy, it turns out this is actually 1. And so, I mean, yeah, so in other words, basically the argument why this works is the after normalizing by the L1, some of the buckets are going to be over here, some of the buckets are going to be over here, but the median of 1 over epsilon squared trials is going to be within minus epsilon. It's going to be within epsilon, 1 plus or minus epsilon of 1 after normalizing by the L1. And so that bucket will be a 1 plus or minus epsilon approximation. This just uses the fact that the distribution is concentrated, so if you take enough elements, the median of them is going to be close to the actual median. And so the theorem for general turnstile streams is that you can implement this algorithm using limited dependence, and by limited I mean log over 1 over epsilon, so that it's still a 1 plus or minus epsilon approximation. Again, when you have this limited, what did I just do? I don't know, did anything. Cool. Anyway, so again, note that. Sorry here. Yeah. So it's actually a little bit of a lie in the sense that to get away with using log 1 over epsilon as independence, you have to actually use a slightly different estimator. It's called the log cosine estimator. Basically, you take the log of the cosine of this thing. It's really the same idea though. It's basically you're taking the median of these bunch of buckets and applying some continuous function to it. Using limited independence to show the result still holds. So we have 1 over epsilon squared buckets. Each bucket is a log n bit integer. Space is 1 over epsilon squared times log n. Okay, yeah, so the observation that you need to see to figure out how we can estimate this value on bounded deletion streams is that every single one of these buckets, yi, that we're storing, it's the dot product of a row of m and the frequency vector, right? So you can actually think of this dot product as just a stream on one item, right? Where a positive update is insertion and negative update is deletion. So it's just a stream on one item, and you look at, you can then define the insertion and deletion vectors of that item for the ith bucket. And so what we want to show is that this bucket has like the alpha property, so we can estimate it. So what we do is we say, okay, so look at that, look at the value of the bucket. Sorry, this is the number of updates to that received to that bucket. I tilde I plus d tilde I. We want to show that that doesn't explode too much more than the number of updates made to the stream. The number of updates made to f is I plus d, but then we're scaling all these updates by these mi's. So we want to look at the blow. How much of it is there a blow up? It's actually not too hard to show that. So if you condition on none of these Cauchys being too large, like I can say with high probability, none of these Cauchys are going to be more than n to the 5, because I only have like n log n of these Cauchys. Then actually it does have an expectation. The expectation is log n. The expectation of the actual value is going to be like log n. And then just using a Markov bound, like a simple Markov bound, you can show that you're not going to get more than a poly log n over epsilon blow up over all the 1 over epsilon squared buckets. But then we know that our stream to begin with had the alpha property. So that means that actually the number of updates to each bucket is not only a poly log n blow up times the number of updates to begin with, and that's in turn alpha times the L1 because of the alpha property. And so altogether, we know that the number of updates is still, this bucket still more or less has the alpha property. The number of updates, sorry, it has the alpha poly log n over epsilon property, because the number of updates made to the bucket is times the, actually, sorry, that's not entirely true because the bucket can be smaller than the L1. But in essence, all I'm doing here is I'm upper bounding the number of updates that were made to that bucket. And my goal is going to be to estimate the bucket by sampling, right? And my error is going to be a function of the number of updates. It's going to be epsilon times the number of updates, where epsilon goes into the log. So what I can do is I can just set epsilon to be, poly log n over epsilon, sorry, poly epsilon over log n over alpha, and then my error will be epsilon times f1. So what I'm going to show is, yeah, what I just said, is we can sample updates to these yi's. So I just run the same algorithm I was running before, but every time I would have updated one of the buckets, I just flip a coin with some probability and decide whether or not to sample it. And we can do a similar sample procedure that I talked about in the count sketch. And then we get additive epsilon times F1 error using this much space for every bucket, because the counters are going to be the size of poly alpha log n over epsilon. So we obtain a full vector of estimates, and each estimate is going to be epsilon, an epsilon approximation times the L1. But recall that each of these buckets was supposed to be more or less the L1. These buckets are basically our estimates of the L1. So the algorithm, so this is going to be an epsilon approximation. So the algorithm is to do the same things before, create this matrix of Cauchys. We have log 1 over epsilon y dependence. We sample updates to all the buckets, and we obtain these tilde iys that are estimates of the y's of the original algorithm. And then we just output the same thing, but with our estimates. And it's easy to see, like, if we had a bunch of items before, and then we get an epsilon F1 error on all of them, the median of this new set of buckets is going to be most epsilon times the L1 of plus, you're most going to get most additive error by taking the median. Because each item is going to be shifted by most that, so the median is going to be shifted by most this. Again, we're actually using a log cosine estimator, but the same idea holds. So you output the same thing, and this is going to be a 1 plus or minus epsilon approximation of the same thing if you had the yi's, not the y tildes. And because that algorithm works, our algorithm works, is the more or less the intuition. So for an alpha property stream, this estimator is a 1 plus or minus epsilon estimator of the L1. And so there's a slight difference here. We don't actually completely remove the log n factor. So the cost of the buckets is 1 over epsilon squared times the bit size of the bucket. But we still have to store 1 over epsilon y's independence. So to do that, we have to use hash functions, and there's n variables, and we have log 1 over epsilon y's independence. So to create a hash function on a universe of size n that is log 1 over epsilon y's independent, you need log n, log 1 over epsilon bits. But what we have done is we've separated the dependency on epsilon. We separated the dependency more or less on epsilon linearly, linear terms of epsilon and log n. And this beats the lower bound, which is epsilon 1 over epsilon squared log n for general turnstile streams. And we also have a matching lower bound up to log 1 over epsilon terms for alpha property streams. It shows that this is essentially type. This is actually getting divided by log 1 over epsilon, but I omitted that. It doesn't really matter that much. Anyway, so this is showing that another problem, we can also use sampling to reduce the counter sizes and give estimates for these bounded deletion streams that use less space. And so in our work, which basically on the archive soon, but not quite yet, shows that you can actually get this same reduction that I just said, which is taking the log n factor and the best lower bound for turnstile streams, and replacing it with a log alpha factor for all these problems. So for the heavy hitter problem, we do this. General turnstile means that at the end of the day, the coordinates can also be negative. It's just a slight generalization, but for all these, this shows what case we're in. So if you do that for inner products as well, we remove the log n factor and replace it with a log alpha factor. And for L1 estimation, L0 estimation, sampling problems as well, we also get improvements of log n to log alpha. And for all these upper bounds here that we have, we also have up to log 1 over epsilon terms matching lower bounds for the alpha property for any alpha constant to poly n. So yeah, so these are the results.
Question?
Do something to decrease the, can you still make this work with KY's epsilon bias
so you're not saying approximate independence, you're saying the sampling is approximate. So you're not saying like epsilon approximate log 1 over epsilon y is independence. You're saying there's like epsilon and bias in the sampling.
Yeah.
I'm pretty sure it would be the same, because that would just correspond to if epsilon bias in the sampling, the difference that would be from uniform sampling would be epsilon times the L1 because of the alpha property. The length of the stream, it would be epsilon times the length of the stream, and then you have to make epsilon sufficiently small, and S epsilon times the L1 norm because of the alpha property. So I think that you would get the same thing.
Okay, if there are no more questions for the